Now, come on, I thought the show could use a pop of color. Maybe we should leave the color to our next presenter, Kyle Denton.
Fine. Alright. So a really common question among bored and curious minds is if we all experience color the same way. For example, is the red that I see the blue that you see? And I'll get to this question at the end of the talk. First, we have to address what color is. And as some of you might know, color is just light. And light is part of the electromagnetic spectrum. So colors, in a sense, are just waves of energy. We are just bodies in space with objects surrounding us. However, our brain can interpret this energy that enters our eyes and perceive it as the things that you see around you. How do your eyes do this though? When light enters your eyes, it hits the back part of your eye called the retina. And the retina is lined with cells called rods and cones. The rods are primarily used to detect the amount of light, and the cones are used to discriminate between different colors. These cells are coated in proteins. The rods are coated in rhodopsin, and the cones are coated in opsin. And these proteins react chemically with the light that enters your eyes to produce an electrical impulse that travels up the optic nerve and into your brain where it then interprets it. We have three types of cones, a red cone, a green cone, and a blue cone. And from just these three primary colors, we can see the millions of colors around us. How do they do this though? Well, each cone and the pigment on it, or the protein on it, has a different sensitivity to a different wavelength of light. So 400 nanometer wavelength will excite your cones differently than a 700 nanometer wavelength of light. Also, I would like to point out how close together the red and green peak sensitivities are. When the genetic information for the proteins on the cones is mutated or not there at all, we refer to this as color blindness. And normally we think of color blindness as red-green color blindness, which is the most common type. The genetic information for the red and green proteins is located on the X chromosome, which is why it's more common in males. But why is it there in the first place? Well, this goes back to evolution. In early societies, we would have been hunters and gatherers. The women would have more likely been the gatherers, so it would have been beneficial to be able to discriminate colors better. So, to see a red berry on a green background, for example. Also, we used to only have two chromosomes, or two cones, a blue cone and a yellow cone. And at one point, the yellow cone split into the green and red cones that we see today. And this is why I think our artist color wheel varies from the actual color wheel. As you might be able to see, on the artist color wheel on the right, the red and green area covers up almost half of the color wheel, versus in reality, it's almost only a third of our vision. So back to color blindness. On one of these diagrams, you'll see varying bands. I'll zoom in so you can see. Each of the bands represents hues that a colorblind person will not be able to discriminate from each other. These bands can vary in thickness. For example, if they're very thin, a colorblind person might only have a mutated protein, versus if they're very thick, a person might have no information for that cone at all. So what might it be like? As you probably can recognize, the top left corner is normal color vision. And then top right corner is red color blindness, bottom left is green color blindness, and the bottom right is blue color blindness. You might be thinking that the red and green color blindnesses look very similar, and they do. This goes back to the fact that the red and green cone peak sensitivities are very close together. Missing the information from one or the other is not that important to your color vision. This table shows the relative frequencies of the different types of color blindness. The main thing I want to point out here is how uncommon the blue color blindness is. This is the tritanopia and tritonomaly. The reason it's so uncommon is because the genetic information for the protein on the blue cone is located on the 7th chromosome, which is much less likely to have mutations on it because it develops earlier in the womb. Tetrachromacy. So color vision can be thought of on a spectrum, having no color vision in a black and white world to theoretically infinite primary colors. We have 3 primary colors, but pigeons, for example, have 5 primary colors, and some fish and other birds have 4. And it's also theorized that some members of the female population have 4 chromosomes, or 4 cones. Our color vision can be thought of in a diagram like this, where the X, Y, and Z axes are replaced with red, green, and blue. In this analogy, tetrachromacy is the fourth dimension of color. How might this happen? Well, it all comes down to the fact that females have two X chromosomes. If they inherit 2 copies of the blue genetic information and 2 copies of the green genetic information, 1 copy of the regular red information, and the varying mutated copy of the red information, their brain might process this as 4 different photoreceptors. It's theorized that 12% of women might have 4 different cones. However, obviously not 12% of women can discriminate these 4 primary colors. And this is probably due to the fact that the 2 red informations aren't sufficiently different from each other. There have only been 2 or 3 confirmed cases of tetrachromacy. This painting on the left is done by a tetrachromatic artist. As you can see, the depth of color and hues that they see is much greater than what we see on the right. So, back to my original question, do we all see color in different ways? I can't answer, is my red your blue, and science may never be able to confirm this or not. However, I guarantee that the maroon that I see is different to a colorblind person and different to a tetrachromat, and I think that's pretty interesting. Thank you.